Um, Good morning. So let's go ahead and get started. So let's talk about some stuff for lesson 31. But before we do that, a couple quick announcements. So quiz 11 is going to be, well, opens today, covering lesson 29, and closes tomorrow. Quiz 12 is going to be on next Monday. That's when it opens up, and closes on Tuesday the 24th, covering lessons 30 and 31. So basically the definite integrals lessons. So, yep.
Where's our class? Where's our class?
I have no idea. It was like 8:31. No one was here. I'm like, well, I'm just gonna get started. I don't really care. Also, I apologize for the really awkward yellow color. But yeah. Anyways, so I guess now that actually people have shown up, do you guys have any questions on the homework?
No.
Okay, cool. So, so you guys know the quizzes that are coming up. So, all right. So let's go ahead and look at that. So now we have that, lesson 31. Let's go ahead and do a quick recollection from last time. So the definite integral, from integral from a to b of f of x dx represents the signs. I'll give you guys a second to. No, you're fine. Okay, so also one more announcement, Zoom office hours on Friday. So in place of the ones that will not happen tonight. Yeah, so back to this. So the definite integral from a to b of f of x dx, like we said, represents the signed area under the curve y equals f of x on the interval a comma b. Okay. So just to give you a quick idea of what that means. So we have this curve y equals f of x, and we put a here and here. That means that, and put x equals a and x equals b here. The area we're looking at is this part right here. Okay. All right. So last time was spent focusing on, how can we find definite integrals based off of geometric formulas. So now we're actually going to focus on specific properties of definite integrals. Okay. So here's what I mean by this. So one of the important ones is if we take the integral from a to a of f of x dx, well, what you'll notice is that this is going to actually end up being 0. And here's why. So the thing is that if we take our function f of x again, so y equals f of x, and we put a here, all that really means is that we're just integrating a line, essentially. So, integrating over a line. But here's the thing. If we're integrating over a line, what is the area of that? If we integrate over just a line. Does it even have any area? It doesn't have any area, right? It has no area. Okay? So because of that, if we're just integrating over a line, then we have no area, or has area 0. So basically what you're going to get is that the integral from a to a is going to end up being 0 from this. Okay? So the second one, or I guess the next two, are going to be we're going to follow from what we have from indefinite integrals. So same as indefinite integrals. Okay. So we had the integral from a to b of f of x plus or minus g of x dx. So that's going to be equal to integral from a to b of f of x dx plus or minus the integral from a to b of g of x dx. Okay. So like I said, this is the same property that we had with the indefinite integrals, just without the bounds here. And similarly, if we have the integral from a to b of k times some function f of x dx, what we can do is, like we have with indefinite integrals, we can take this constant out if k is constant. So k times the integral from a to b of f of x dx with k constant. Okay. So those are the two properties that we have from indefinite integrals. So the next one I want to focus on, or the next two, are going to be something we haven't really seen before. So the next one, 4, what we'll do is if we choose three constants, we have a less than equal to b less than equal to c, just three constants. We have the integral from a to c of f of x dx is equal to the integral from a to b of f of x dx plus the integral from b to c of f of x dx. So this is one of the properties that's sort of exclusive to definite integrals, not sort of unlike 2 and 3 here. So pictorially to see why, consider this. So we have a, we'll put a, b, and c here for y equals f of x. A, B, C, A, B, C, f of x, and then a, b, c here. Okay, y equals f of x. Okay, so here's what we're going to do with this. So for this first integral, well, we're integrating from a to c here. So what that tells us is that we should have this integral here from a to c. So the total area is going to end up being all this. Okay, so all right, nothing too crazy there. But now for this next one, we're integrating from a to b. So what we end up with is that this integral just corresponds to this part right here. But the thing is that this integral from b to c, meanwhile, simply corresponds to this part right here. So pictorially, that sort of gives us a sort of pictorial explanation as to why this property holds regarding definite integrals. So what that tells us is that, all right, well, if we have the integral from a to c here, we can sort of split this off into two other integrals here. So that's sort of an intuitive explanation as to why we have this property here, sort of pictorially speaking. Okay. And the last one is going to be if we take the integral from a to b of f of x dx. Well, we say, all right, well, in this case, one thing that could help us is that this is the same thing as the negative of the integral from b to a of f of x dx. So this one is a bit trickier to explain without knowing the fundamental theorem of calculus. So for now, all I'm going to say is that check this with fundamental theorem of calculus next time. So that's all I'm going to say on that property. Okay, so now that we have all these properties, let's see how we can apply them. So for example 1, we're saying, okay, we're given 3 integrals. The integral from 5 to 9 of 2x cubed dx is 2,968. The integral from 5 to 9 of 3x is 84. And the integral from 5 to 9 of 1 dx is 4. So we're tasked to find these 3 integrals here. So first off, let's start with part A. So part A says we're tasked with finding the integral from 9 to 5 of 2x cubed dx. Now we realize, well, wait a minute. We don't have the integral from 9 to 5, but we do have the integral from 5 to 9. So which are the properties that we just established do you think we could use to figure this out?
Number 5.
Number 5, right? Because in this case, what this allows us to do is just take the negative of this while flipping the bounds. So in this case, we have the negative of 5 to 9 of 2x cubed dx. So that's just negative 2,968. Okay? So part A wasn't too bad. So part B though, so let's see. Now in this case, we do have the integral from 5 to 9, which is consistent with the bounds we have here. But here we have 12x cubed inside our integral. So any thoughts on how we could figure out the value of this guy given the data we have? Actually, you can go ahead.
Oh, wait.
Yeah, I thought you had your hand up.
Would you multiply the first one by 6?
Yes, because what happens is that, well, we don't have the integral of 12x cubed, but we do have that of 2x cubed. So if we were to multiply this by, if we take out a factor of 6 here, so we have 6 times 2x cubed dx, then using property 3 here that we've established before, so property 3, says, all right, we can take out this 6 and say, all right, this is 6 times the integral from 5 to 9 of 2x cubed dx. So since we already know that this integral here is just 2,968, all we have to do is just multiply those two together, and that gives us our answer, which ends up being 17,808. Okay. Oh, now we changed to white. Okay. Okay, it was originally this weird yellow color, but now we're back to regular white. Alright, whatever. Okay, so that's part B. So now part C is a bit more interesting, because now we have the integral from 5 to 9 of 6x cubed minus 6x plus 7. So the thing is that because of property 2 that we have, well, that seems to suggest that, like we've been doing with indefinite integrals, we can sort of focus on each of these terms, the definite integrals of each individual term. So what that means is that, we can take the integral from 5 to 9 of 6x cubed dx minus the integral from 5 to 9 of 6x dx, and then plus the integral from 5 to 9 of 7 dx. Okay. So we say, okay, so now that we have that, if we use similar reasoning that we utilized in part B, how can we figure this? How can we figure out the value of this integral?
I mean, we have the of the 2x cubed and then 3x and all one, so we can do the same thing we did in part B for each one.
Okay, so so in this case, what constants would you pull out from each of these to get what we want?
3 and 2 and 7.
Right, so in this case, for the first integral, we got to pull out a 3. So we have 3 times the integral from 5 to 9 of 2x cubed dx. Minus, in this case, you want to pull out 2. So we have 2 times the integral from 5 to 9 of 3x dx. And then plus this case 7 times the integral from 5 to 9 of 1 dx. Okay, and now that we have all three of these numbers given to us, we can say, all right, well, this is just 3 times 2,968 minus 2 times, well, 84, plus 7 times, well, 4. Okay? So if we put all this together, well, put this giant number together, well, put that into a calculator, you should end up with 8,764. Okay? So that's example 1 in a nutshell. So any questions on that part before we move on? So, what you may have noticed up until this point is that the only big property that we haven't really used yet is property 4. But now we'll have a chance to do that. So, example 2 says, given real numbers a, b, and c, with a less than equal to b less than equal to c, and the integral from a to b of g of x dx is equal to 3, and the integral from a to c of g of x is 8 times the integral of this guy right here. So integral from a to b. We're tasked with figuring out the integral from b to c of g of x dx. Okay? So we say, all right, well, first off, we should probably figure out more explicitly what this guy is, because even though we have the integral of this guy right here, of integral from a to b, we don't explicitly have the integral from a to c. So, using the data we have, you should be able to pretty quickly figure out that the integral from a to c is equal to what numeric value, given the data we have. So, if the integral from a to c of g of x is 8 times the integral from a to b of g of x, it's 24, right? So it's 8 times 3, so 24. So in this case, we say, all right, we're given real numbers a, b, and c with a less than equal to b less than equal to c. So in this case, if we use property 4 now, based on this premise, then what we get is that, all right, well, we have the integral from a to c of g of x dx is equal to the integral from a to b of g of x dx plus integral from b to c of g of x dx. Okay? So that says, all right, so we have the integral from a to b and the integral from c to a. So now all we have to do is figure out, well, what is the integral from c to b? So in this case, we say, all right, well, using the data we have, well, we know that the integral from a to c, as we just established, is 24. So put that right here. And the integral from a to b is 3. So all that we have to do is figure out, well, what's the integral from b to c? So integral from a to b is 3, as we just established. So now what we have to do is figure out, well, what's the integral from b to c of g of x dx? Okay. Okay. So you probably pretty quickly figure out at this point, well, that's just 21. So 21 is the integral from b to c of g of x dx. Okay. Yeah.
I don't really understand how we have to find the integral of a to c, because isn't it just given that it's 8? Or no?
Well, it's 8 times this. Oh, so yeah, so in this case, the integral from a to c of g of x is sort of supposed to be 8 times this.
I didn't see that. I thought it just equaled 8. Okay.
Oh yeah, no, sorry, probably should have clarified that, my bad. So yeah, so in this case, the integral from a to c is supposed to just be 8 times this. So that's all it means. So. Okay. So any questions about any other questions about example 2? Okay. So one quick little remark I want to make on this that will be relatively important is that one of the big reasons why I focused on property 4 with this assumption here is so I could make things a bit easier to visualize what's happening. But it turns out that property 4 still holds even if this assumption here is not being made here. So remark. Property 4 holds for any A, B, and C. So don't need A less than equal to B less than equal to C. Or at least it's not needed. The only reason I did that, okay, if I can spell it there. So the only reason it was done before was to make the statement easier to visualize. Okay. So, like I said, this can hold for any A, B, and C you throw at it. But like I said, the only reason I put this assumption here before was just so that way I could make the statement easier to visualize. Okay. Because the thing is that it will be helpful to drop this assumption when we get to the next example. So that's the only reason I put this remark here. So. Okay. All right. So any questions on any of that before we move on? Okay. So here, with example 3, we say, all right, if the integral from -4 to 2 of f of x is 9, the integral from -3 to -5 of f of x is 2, and integral from -5 to 2 is -3, we have to find the following. So we have the integral from -3 to +2 of f of x dx. So starting with this one, we say, well, all right, so based off of all the things that we have up until this point, all the properties, it doesn't really look like we have one that really works here. So at least not immediately. So in other words, we can't really use property 5 because there's no integrals here given with these exact bounds. So property 5 doesn't help us here, not immediately anyway. And there's nothing to sort of add, no integrals to add, subtract, or multiply by some constant, so 2 and 3 don't help. So it looks like our only real option is to use property 4 again. So use property 4 again. Use property 4 again, since others don't seem to help. Okay. So in this case, we say, all right, well, if we do that, we have the integral from -3 to +2 of f of x dx is the integral from -3 to some value b, which we'll figure out later. So let me just put this in red. So the integral from 3 to some value b of f of x dx plus the integral from b to 2 of f of x dx. So we say, all right, well, based off of this, we can say, all right, well, is there a value of b we can use based off given data. Okay? So if we take a look at what's given to us, we say, all right, well, if we take a look at what we have here, it looks like we're going to need to figure out, we need a definite integral with one bound of 3 and another with a bound of 2. So based off of that, we say, all right, well, what value b do you think will help us out here based off of the given data? -5, right? Because here we have a integral with bound -3, and we have a bound with an integral with bound 2. So if we use b equals -5, well, then we have -3 to -5 of f of x dx, plus the integral from -5 to +2 of f of x dx. So then we say, all right, well, we know what these are. So we have 2 plus -3. So that should pretty quickly give you that your integral that you want is -1. Okay. So that's part A. So any questions on part A before we move on? Yeah?
So -5 is smaller than 3, so can you still like have the...
Yeah, so like I said, the remark here says we don't have to worry about, anything. We don't have to worry about the bound with this value of b here being smaller than -3, or we don't have to worry about where exactly it lands on the real number line. So like I said, we don't need a greater than or equal to b, less than or equal to c. So we don't need a less than b less than c. So this holds for any a, b, and c you want here. That's all. That's the reason why we're going to make this remark here, precisely for this.
So like a doesn't have to be like bigger than b.
Nope. Not in this context. So in this case, we can have a, b, and c be whatever numbers we want. So, like I said, the only reason I made that restriction before was because that was made to make the statement easier to visualize. Okay. So any other questions on that? All right. So part B should be relatively quick. So if we take a look at what's given to us, does it look like there's any integrals that we can use here to help make our lives a bit easier here?
The first one?
Yeah, the first one, right? Because we have integral from -4 to +2, so of f of x. So how do you think we can get the integral from 2 to -4?
You flip it, so you flip the sign.
Yep. Flip the bounds and throw a negative sign outside. Yep. So we have integral from -4 to +2 of f of x dx. So that should pretty quickly net you a -9. Okay, so that's part B. So any questions on that one? Okay. So the last one we'll focus on. Is part C. So we have the integral from -3 to +4. So it looks like since we don't have any integrals with these explicit bounds, it looks like our only option is to use property 4 again. So property 4 then. Okay. So we have the integral from -3 to some value b of f of x dx plus integral from some value b to -4 of f of x dx. Okay. So if we use similar reasoning as part A, so what value b here do you think we'll want to use here given the bounds that we have? Or I guess it should say, given all the data we have, given that part A was -1. yeah, you want to use 2. So it seems like b equals 2 is your best option. So the integral from -3 to positive 2 of f of x dx was integral from 2 to -4 of f of x dx. Okay? So the good news is that, well, we got the integral from -3 to positive 2 as per part A, so that's not too bad. So then we realize, oh, wait a minute. We also have the integral from 2 to -4 as well as per part B. So we have -1 here and then plus -9. So -10. So this is from part A. And then this is from part B. Okay. Right. So that's example 3. So any questions on any of that? Okay. So as you may have noticed, example 4 is available as well. So for this one, I have it's a group work / try on your own problem. So would you guys want to try this one on your own for a bit, or do you guys want me to help you out a bit first, based off of what's happening here? So we have the integral from 0 to 7 of f of x is 5. Integral from 0 to 4 of f of x is -3, and the integral from 7 to 4 of g of x is 3. We have to figure out integral from 4 to 7 of 2 times f of x minus 3 times g of x. So why don't you guys take some time to figure this one out? I'll give you guys about 5 minutes. So we'll reconvene at about 9:08. That would be pretty. Oh, whatever. Well, I'll just tell you when there's a few minutes remaining. It's 9:04 right now. well, looks like people have their pencils down, so we'll go ahead and reconvene. So first off, well, what, did you guys get any number out of this?
I got 15.
15. Not quite what I got. Let's go ahead and talk about this. So let's see. First off, so what we notice here is that we can sort of rewrite this in a slightly different way. So we notice is that this is the integral from 4 to 7 of 2 times f of x dx minus the integral from 4 to 7 of 3 times g of x dx. I guess did anyone else have a value?
I got 13.
I got 23. I got 25.
That seems to be closer to what I got. Let's talk about this. So we have 2 times. So if we take out the constants here, so we got 4 to 7, or 7 to 4. No, 4 to 7. I'm awake, I promise. So the integral from 4 to 7 of f of x minus the integral minus 3 times the integral from 4 to 7 of g of x dx. So we say, all right, well, it's good enough we got this, so now we got to figure out, well, what are these guys equal to? So we say, all right, let's take a look at the integral from 4 to 7. So how would we want to figure this integral out? So we say, all right, the integral from 4 to 7 of f of x dx is integral. So let's see. Based off of the given data we have here regarding f of x, how would we want to evaluate this thing?
The property 4 thing, so the integral b to 4 of f of x plus the integral of 7 to b.
Okay. Close. So in this case, you want to use, you do want to use property 4 again. Property 4. Okay. So in this case, remember, property 4 states that you have the integral from 4 to b of f of x dx plus the integral from b to 7 of f of x dx. So in this case, given the data here, what value b should you be using here?
0.
Right, should you be using b equals 0. Okay, so we have integral from 4 to 0 of f of x dx plus integral from 4 to 7 of f of x dx. Okay, so here we have, all right, so, sorry, 0, my bad. Should be 0, my bad. So we have the integral from 4 to 0 of f of x dx. So what would that equal?
3.
Yeah, 3, because here we have the negative of 0 to 4 of f of x dx, which we already have as, this part here is just negative 3. We focus on this integral here, plus integral from 0 to 7 of f of x dx. So we got negative of negative 3 plus the integral from 0 to 7 of 5. So that is just going to be a big resounding 8. So that's that. But thankfully, the next one, meanwhile, should be much quicker for g of x. So we got integral from 4 to 7 of g of x dx. So given our data, what would that equal? Negative 3, right? Because we have the integral from 7 to 4. So all we have to do is just put it negative here, flip the bounds, and we got exactly what we want. So this is just negative 3. Okay, so what that tells us is that, all right, we got 2 times 8 plus, minus 3 times negative 3. Okay? So we say, all right, well, noting that we have 2 negatives on the second term, we can cancel those out. So we end up with, 16 plus 9, which is just 25. So this is the final answer you want here. Okay, so So that's how we get 25 out of this. Okay, so any questions on that part? Okay, well, that's all I have for today, so, yeah, question?
Can you go to the first page?
Oh, yeah, sure. So I guess if there are no other questions, I'll go ahead and leave up page 1 for you guys that showed up a bit late, and I'll go ahead and call it here. So otherwise, I'll have, like I said, I'll have office hours over Zoom on Friday and not tonight. So just keep that in mind while you're doing homework.